Okay, so I believe this will be our last lecture on a CFT in higher than 2 dimensions. And I'm just gonna continue the discussion of the classical energy momentum tensor from the previous lecture and introduce the one identity, especially for the scaling current, and say a few things about scaling invariance at the quantum level, okay? As an extension of the studies we started in the previous lecture. Okay, so just to remind where we stopped, we started from considering space-time symmetries, and for space-time symmetries, another theorem gives this conserved current in general, okay, for any infinitesimal space-time symmetry that in general depend on x local transformation. Okay, the concept the node current had this form where delta phi is the transformation on the field induced by the space-time transformation itself. But we also, in general, will get an additional piece here that is an internal transformation. Okay? It's an internal transformation. Internal transformation means a transformation in the space of field itself. Okay? When we did the rotations, this corresponds to spinning. Okay? You get the spin representation matrices. Unless, of course, you're dealing with only scalar fields, then this internal piece for rotation doesn't show up. And we saw that additionally for scaling transformations, we also have an additional contribution that depends on the scaling dimension delta of the field. Okay? And also, so we will be present for scalar fields also, okay? Contrary to spin when considering scalars. And then again, specializing for scaling transformations, then should have written x prime mu equals okay. I'm just missing the side point. This for the scaling transformation, this corresponds to our epsilon, and it depends linearly on spacetime, on the spacetime point. This induces this transformation on the field, this external transformation, and this internal transformation, okay, in the space of fields. And then just plugging this all together here, and reminding the definition of the canonical energy momentum tensor that arises when considering translations in the same fashion. We can write the scaling current in this form. I usually call scaling use the word scaling instead of dilatation because just a preference of mine, because dilatation gives the impression that it can only increase the distance, it can also contract. But I'll write with a D here for dilatation because it's the common practice. Okay. That's a common.
Or just there's some signs of no, I guess. But yeah.
Well, that might be so.
Yeah.
I did this kind of top of my head. But you signed it.
Like if I look at the T how it's defined, so if I see write the delta phi as a minus lambda, no?
With a minus.
So you have the same
sign. Minus here.
Yeah. So
it's minus about this.
With this minus, you get a minus.
Yeah, because you get a minus there.
And a minus there, so you do have the same.
Probably it's a plus.
Yeah.
You have this form, okay? And the conservation of this current, okay, this current will always be conserved because it follows from another theorem. It is a conserved current. So this conservation law, okay? This way from another theorem implies.
So there should be no understand. Okay.
So conservation of this another current implies when you use its explicit form, implies that the trace of the canonical energy momentum tensor has this form that depends, again, just to emphasize the internal part of the transformation. Okay? The analysis of this for rotation is, again, if you have spinning fields, say a Dirac Fermi or a gauge field, whatever, spin different than zero, then for the rotation current, you would obtain that the an anti-symmetry for the energy momentum tensor that depends on the spin. Okay? This is the analysis for scalings. And again, as in the case for rotations, there was an improvement procedure, the Belli funded improvement that furnishes a symmetric energy momentum tensor, which you do want because many of general relativity, you know that the source of gravitational interactions are conserved symmetric energy momentum tensors. Okay, and then we asked if such an improvement, if there is such an improvement for scaling currents, okay, in order to get rid of this internal part and obtain a new energy momentum tensor that is traceless. Okay, and as we discussed too, this would imply, at least at this classical level, that the theory, if you can make this improvement, then this will imply the scaling in that theory will also imply full conformal invariance. Okay, so the question has deeper consequences, and we saw that there is an improvement procedure which mainly has two steps. The first is to check. You must check if indeed your theory has scaling symmetry. Okay, so just check if your action has scaling symmetry. This is the first step. If the answer is yes, then you must compute the virial, which in the previous lecture I believe I called it delta mu, but the standard name we give it, which I'm going to adopt in this lecture, so you may want to go back later and correct. We usually call it capital V. Okay, you usually compute this virial, which is given by this formula. It's the internal part. Well, in general, it goes with the internal transformation of the fields. If you want to compute the virial for the rotational symmetry, then you obtain some spin matrices here. But in the case of scaling symmetry, this is just simply, and I guess make this my. I'll be missing from my receipt. Okay. For the case of scaling current, the virial is this. Okay, the scaling dimension. And I did not show you all this. I did not give the proof. The complete proof is painstaking work, but the result is that if you can write this virial current as a divergence of some other two tensors, like this, then you can improve your energy momentum tensor. Okay, that means that you can define an improved energy momentum tensor. We showed just the note without the C. We can define a new energy momentum tensor such that it is traceless. Okay, and again there is a formula for an explicit formula for the improvement, which is kind of big. In the case of the rotation, it's just like three terms that were like essentially the virial, but with some permutation of indices. Okay, it is essentially kind of the same thing here, but it is way bigger. But there is an explicit formula. But you do not need the explicit formula to check if you can improve it. Okay, this is just to know if you can improve, which also means then this also means that scaling symmetry implies the full conformal conformal symmetry. Okay? If you can indeed write the figure as a divergence sum of the two tensors. And just again to emphasize, this is the classical level. I guess I did not emphasize this as much in the previous lecture, okay? This is just at the classical level. And we looked at the simplest example, which is the scalar field. And, well, I might miss a few functions here again because I'll do this from the top of my head. But in d dimensions, if we had this action with some potential like this, some power law. Okay, this isn't what the way I did in the previous lecture, but the end result is that if you want to stick to polynomial interactions only, then the general solution to that is you only have like this. Okay. You only have conformal symmetry. There are only three solutions to this in order to have conformal symmetry. It is if you're on 3 dimensions, then you can use potential as the 6th power. If you're on 4 dimensions, you can use a quadratic potential, so like lambda by 4 potential. It's the most famous example. Or if you're on 6 dimensions, you can use a cubic potential. But then this will be dangerous because the potential will be bounded from below. But okay. If you do this exercise for this potential, you get some equation relating d and n. And this, if you're looking only for solutions with integers for both d and n, meaning of course integer dimensions of spacetime and polynomial interactions only, then these are the only 3 solutions. Okay. For in order to have conformal symmetry, again at the classical level. Okay, this rules out, for example, the famous Wilson-Fisher theory, which is a fixed point. It has conformal symmetry because in the Wilson-Fisher we have would be at 3 dimensions with a quadratic potential with a master. Okay, this doesn't show up here because purely quantum. Depends on the quantum properties, and you must do a renormalization group study. So it doesn't show up here in this classical analysis. Okay, this is again all at the classical level.
So sorry, I mean this would already break scaling variance. Or what did you say? No, sorry.
Which part?
You just said it also doesn't apply for massive theory. Or, no, sorry. You can just say again what you said.
Which part? I said all of it. About this 3 solutions?
No, the 3 solutions clearly.
About the Wilson-Fisher?
The Wilson-Fisher, yeah.
Okay, the Wilson-Fisher is I never know this. With an S, like this? With this a C?
Fisher, yeah.
Is it like this?
I think it is.
I never know.
Yeah.
But okay, that's not okay. The Wilson-Fisher theory is on 3 dimensions. So you have the kinetic term, you have a master, and you have a potential, right?
Yeah.
And the point is, we know this is a, if you study this as a quantum field theory, you find a fixed point. Okay, somewhere in the space of parameters there will be a fixed point, and this has a conformal symmetry.
Oh, okay. So you talk, because this action is not scaling variant.
Yeah.
But
you know you have
effect
conformal because it's a quantum effect. You can compute the beta functions and see that there is a point in theory space where the beta functions vanish. And then you can show that it also has conformal conformal symmetry. What I was saying is that this solution doesn't show up at the classical level, precisely because you must go to the deeper level, you must go to the quantum level. Okay? Because in 3 dimensions, if you put a quartic potential, at the classical level, if you put a mass term, then you won't have scaling symmetry.
Yeah.
Okay, and you have a mass term here. Okay, so not all possibilities are envisaged here in the classical study. Okay.
But so I thought that, I mean, the class, what confused me is, I mean, from classical it doesn't follow that they have scaling variance on the quantum level, but if you have it on the quantum level, you should also have it, of course, on the classical level, no? I mean, so this with a finite mass, no, I mean,
no, I'm not understanding your.
So I'm just this action that you write down there was infinite great scaling variance. So it has no scaling variance.
Yeah, if you do a classical analysis,
but
you don't have scaling variance.
But even if I don't get it. I mean, it doesn't have scaling variance, so it doesn't have conformal variance on this classical level, which also implies that it can't have can't have conformal variance on the quantum level, because I mean, isn't it like, maybe I'm thinking wrong, but isn't it like I have a symmetry on the classical level, then it could be that I have some anomaly which would.
Yeah, that's one thing.
Yeah,
you may have classical symmetry that does not carry over to the quantum realm.
Yes.
Okay? That would be an anomaly.
But does it make sense that you have a quantum, that on the quantum level you have the symmetry which you don't have on the classical level?
You don't have scaling symmetry for this theory everywhere in theory space. Okay? There's a specific point where all the quantum fluctuations conspire to produce a scaling invariant. It's a critical point.
So you want to talk about an RG flow where the mass flows to 0 and at this quantum critical point then I can...
But there is officially a fixed point not located at m squared equals 0.
But I just don't get it how... Okay. I mean...
I don't know the values, but
it's a final. I guess, I think so, because otherwise I mean you don't have scaling variance. And how can you then have...
You don't have scaling variance set up?
If you have a massive...
Classical or quantum level?
I think, I mean, if you don't have it on the classical level, you can't have it on the quantum level.
In general, no, but that is not true always.
No. Why? Huh?
Well, because if you do technically if you do an RG analysis...
No, but then you're saying that you're going to an effective theory, we normalize the parameter...
Yeah, the point is, it's basically that the degrees of freedom it would be a strongly coupled theory. So maybe this action was at the classical level. Maybe this action at the classical level does not capture the effective degrees of freedom at the critical point. Okay, we can start with this action.
But then you're talking about
the quantum theory. You study the
some reorganization and you end up with a different theory.
Yeah, you find that there's a fixed point, which is a strongly coupled theory, which this by itself just means that in principle you don't know what are the actual degrees of freedom. Okay, so if you find out what they are, they can probably go back and write another effective classical version, or something like this. I don't know if this has been done. It's a bit confusing.
No, I think I know what you want to say. I mean, you look at the RG, you look where you flow to, you look at some specific parameter point that you flow to some critical point, and there you have a massive theory.
It's because at the quantum realm you have this possibility that the quantum fluctuations might just conspire to produce an emergent scaling invariance at some point. Yeah. The point is that this classical analysis here, if I would just wrote down this say say I did not have the master, and here I put the this case here. Okay, 3 dimensions with a 5 to the 6 potential. Then from conformal, from the classical analysis, then I would have the possibility that the quantum version of the theory has at least this scaling, this full conformal invariance in the entire Fourier space for any values of this wave function normalization and the coupling, the potential. Okay, and then you have to actually do the RG study to see. You have to be careful with the anomalies to make sure that this symmetry, this conformal symmetry at classical level, would carry over to the quantum theory. But so this is always true. This is always a possibility. The classical study would give the classical analysis would say that if these symmetries carry over to the quantum theory, then they could possibly carry over to the entire theory space, okay, for any value of discussions. If it does, there's no anomaly, there are no anomalies, and so on. Generically, you can get strong in couple theories, the new emergent degrees of freedom, and so on, so forth. It's a complicated story. But what the classical analysis misses is that you can have. This is the. I don't know if I'm indicated, but this is the precise point. The classical in the classical analysis, the coupling constants have fixed values. They do not run. They do not float. Okay, so that's why you cannot conclude this backwards. Okay, if I have the symmetry at some specific point in the theory space, in the quantum theory, this doesn't mean that the correspondent classical theory must have this scaling symmetry as well.
No, I understood what, yes. So you can float to a fixed point where you have that. Yeah.
So, any more questions about this? No? Because I don't think I want to say anything else about this specific example. Yeah, I guess not. Okay. But yeah, this is the message. Okay? And there is another example here that is actually Maxwell theory. Okay? We know, I guess everyone knows, that Maxwell theory is conformal at least on 4-dimensional spacetime, okay? Namely our physical group. So let's just check this. Okay? Again, for now, just at the classical level. So of course the action for the Maxwell theory is, okay, this is another example. Maxwell theory. The action is of course just, if you're writing d dimensions, just Poisson force of the field strength squared. Okay, free Maxwell theory. No sources. And the already symmetrized energy momentum tensor, which is a Belli-Fante tensor, is given by this mu. This is the already symmetrized Belli-Fante energy momentum tensor. Okay, we're only going to worry about the traceless improvement of this energy momentum tensor. When can we do this? Okay. So we're going to do basically the same exercise as we did with the scalar field, just a bit more annoying because you have an index structure now, have vector fields, gauge fields, but it's pretty straightforward. The first thing we must check, when does this has scaling variance? And we do the same exercise. We just take x to an x prime. That's just a finite scaling by a factor of lambda. Of course, the derivatives we scale with the inverse power. And but the point is, the series only has a kinetic term. This is a free maximum, and this is always constructed to be scaling variant. The mass dimension of the field is such that this is dimensionless. So all the factors of lambda will cancel. Okay. So yeah, pretty much it has scaling symmetry. For all d, okay, any dimension. Now you just must compute the virial current. Okay, I'm gonna compute this time. That is over there. Okay, this for the max of theory is just seeing how I put in this. Okay, so I just keep the. Let's see if this is traceless, okay? Because if this is traceless, then we don't need to do that, okay? And if you take the trace, then this is basically f squared, right? Nu becomes mu. You already have an f squared here. But when you take the trace here, you obtain a factor of d. Okay? So basically, since they're both f squared, the trace of this Bellin-Fontaine moment tensor is given like this. Okay? So we see that for in 4 dimensions, we have a traceless energy moment tensor. So in 4 dimensions, the free maximum theory is conformal. Okay, this is what we knew. And the question is, can I improve this energy momentum tensor in dimensions different than 4? And if the answer is yes, then what we learn is that maximum theory is conformal in every dimension, just like a free scala would be. Okay? Or if the answer is no, then we learn that the maximum theory is only conformal. The free maximum theory is only conformal in 4 dimensions. Okay, so this is what we're doing here. This is what I started. Okay, so we must compute this. Okay, our field phi is just the gauge field. Okay, and the best way to go about this is to use the chain rule here. Okay, differentiate with respect to the field strength first, then differentiate this field strength with respect to the okay, and this. We get a factor of 2 because we have f squared here. So you obtain minus 1/2 f alpha beta. And then, well, just to remind you, this is of course this curve. Okay, so you just need to match the indices. Okay. And you get an antisymmetric combination of deltas, okay? The first time is you match mu to alpha and mu to beta. So you obtain delta mu alpha, delta mu beta. Then we get this minus over here, and then you match mu to beta and mu to alpha. So you obtain mu beta, delta mu alpha. Okay? Now just do these contractions. And the first one, alpha beta, becomes nu. Then alpha becomes nu, and beta becomes nu. So we have nu. But since the field strength is anti-symmetric, you okay, sorry, minus is plus, then you obtain just minus f mu. Okay. So the virial is this bit here. So the virial is the same bit, mu. I put the scaling dimension nu, delta. This is the scaling dimension of the gauge field, contracted with a nu. Okay. And the point is that you may, I'm going to give you like 15 seconds, but you can convince that this cannot be written in this form. You cannot write this as a divergence. This is not even, well, the delta doesn't matter much because it's just a constant. Okay, you can always bring inside the derivative. Okay. Are you convinced?
This is
well,
this is
the point is that okay, the first term, this term would give something like this. Okay?
yeah.
This you can write as a total derivative.
Yeah.
But the second term, you have this. This you cannot write as a total derivative because the indices are different.
Yeah.
You may want to, I don't know, try and fix some specific gauge, but then it would be an attack of that gauge. It wouldn't be, maybe if you can, I'm guessing. I'm the, have a good.
Yes. Okay.
Are you convinced?
Yeah. Yeah. I mean, yeah. So I'm thinking about gauges, but
Because you only have disputes to play with. Okay.
okay.
You only have mu. It's the only field in your theory. The field strength itself is not of this form. Okay, it's not a divergence. Or if you want to, you have the first time would give something like this. Which is a total divergence, but then you should have to combine with this one with the same mean. I guess. Right, this a square and something like this. To be in that form, something like this, okay? To be in this form. You could do this to the first term, okay? But you cannot do this. You cannot bring this inside here.
No, this
with the same index,
I see, but
the same
I thought I
structure.
could try something more complicated. I don't know. Okay.
That would be one. That's what I'm gonna discuss next.
Yeah.
In 3 dimensions, there is a way to do this. That is what I'm gonna discuss now, unless you have more questions about this. Okay, this was general, D dimensions. So we know that in general, in D dimensions, or different than 4 dimensions, Maxwell theory is not conformal. Okay? Because you cannot write this virial here, you cannot write as a divergence of some true tensor. Okay, this was the test, okay? So, but now I'm gonna tell you a subtlety that can arise on 3 dimensions. I guess I can erase this one. The point is that in 3 dimensions you can, you can increase your theory space in a way to accommodate conformal symmetry. And this is actually pretty simple, but you can escape the first side. It is for 3 dimensions, we have the Hodge duality. This just means the fancy word strength.
But in the end, this is only a topological question, no? I mean, if you're asking if so you have to check first if it's closed, and then if it's closed, you're asking if it's exact. And this is like only quality, or is it? Am I saying something stupid here?
Well, you're doing this homology.
Yes. So it's
for the view recurrence.
Yeah, no, isn't this the question that you're asking? Like, well, I first have to check if it's like, I think a form. So I'm looking if this form that I have is exact.
I never thought about this question in this terms, but maybe you can think. But what I say, you think this because of the divergence, right?
Yeah, I mean, you're asking, yeah, so you're asking if it's exact. So you first have to check if it's closed, so probably it's closed by symmetry, anti-symmetry. Well, I would have to check it actually, but I guess.
Yeah, maybe.
Then
yeah, I don't know. I've never seen this discussion phrased in terms of homology or cohomology.
So probably it's not.
Maybe you can do it. Yeah. But I'm not sure. I've never seen this discussion of improvement phrased. But previously, like I told you, I was gonna send you a paper that was kind of a review of this, and in that paper they do have a more geometrical approach. They review this standard stuff that are presented to you, but then they start talking about fiber bundles and all. I haven't read that, but maybe someone have done this. These guys. I haven't sent you the email because I forgot, because just yesterday I was in control over my emails again. So okay, but I was saying maybe that they can they phrase the same improvement questions in terms of in topology, okay, yes. Using homology or probably homology because it's kind of easy, but maybe there's a way. I have never thought about it this way. Okay. But okay, just returning here for 3 dimensions, we have a this Hodge duality. What does it mean? It means that I can associate. It is a duality between this gauge field and a scalar field. Okay, that is given by. I never know what the factor of half is. Which side? It is. Okay, it's on the other way. Okay. This is anti-symmetric in alphabet. The epsilon tensor is completely anti-symmetric, of course, and then the last thing is I contract with the mu phi. Okay, and the other way is that the derivative. That's what the factor of half. And the factor of half is just because now you're contracting these 2 indexes, so you have this combinatorial factor over that. Whereas you just kind of contract 1 index, so I just have 1 over 1. Okay, so everyone has seen this before? Well, basically what happens is that the equation of motion for a mu becomes an identity. Becomes simply not like this. Okay, and the Young identity becomes the equation of motion for the scalar. Okay, this is pretty common on dualities. Okay, you have the dynamical information becomes an identity. In this case, not topological identity, it doesn't depend on the metric, and the topological identity in the side becomes the dynamic information on the other side. Okay, this pretty common pattern in dualities in general. Okay, and what happens to the action with substitute the field strength with this? We get we just get the free scalar action. That's 3 dimensions. And as we've seen, we can indeed improve the scalar in any dimension to be so that its energy momentum tensor is traceless. Okay? So if you use the hot duality, we can argue that Maxwell theory is conformal in 3 dimensions. And physically, the scalar field just represented the 1 degree of freedom of the photon, okay? Because in 3 dimensions, the photon has only 1 degree of freedom. It only oscillates in one direction. Okay? So physically, this is a picture. More abstractly, theoretically, the point is, what have we done here? We introduced another field. We introduced a scalar field in the theory. And at least the classical evidence does indeed prove that Maxwell theory should be conformal. Okay, so that prescription is a good prescription to test whether or not theories with scaling invariance also has conformal invariance at the classical level at least. But it is not always the whole story. It might have some subtleties like this. So if at least you have some stronger physical intuition, insight, or something like that, you can find some other road. Okay? And there is actually another paper that again discusses Maxwell theory, conformal invariance. It discusses scaling invariance versus conformal invariance for Maxwell fields in any dimension or at the quantum level. And I believe they discuss district 2, but then they also look for higher dimensions. They study the d bigger than 4 dimensions. And I believe that, I'm speaking from the top of my head, I get it wrong, but if I do recall correctly, I guess I find something like for 5 and 6 dimensions you can do some similar thing here, and argue that you can introduce new fields so as to make Maxwell theory conformal. But I don't think it would work for any dimension bigger than 4. And just to give you the kind of the idea is that if you're studying this at the quantum level, you must look to the correlators. And one way to test conformal symmetries, well, you compute, say, the 2-point function, and you can check if it has the form dictated by conformal symmetry. If it does, it doesn't mean it has conformal symmetry, because we would have to look for we have to look for every correlation function, but if it does not, then at least you know that there's no chance.
That's something that I could also, if I look at the 2-point correlation function, somehow you only need it, it looks like, so it looks like it only has the scale invariance, no? So what was the difference between, where did the information on the conformal group enter into 2-point correlation function? I just don't recall. It says like phi of x and phi of x prime is 1 over x minus x prime.
The scaling symmetry, remember the scaling symmetry fixes the power law behavior, exactly. But the conformal symmetry fixes the relation between the scaling dimensions. But of course, if you take the same field,
yeah, exactly. So where does the scaling variance enter then?
That's the point. You have to go you have to check the 3-point functions.
Okay.
That is the point.
Okay.
This is just a short. Okay. If you do not have the power law, then you already know that there is no scaling variance. But if it does have the power law, then you have to keep checking.
But then you have to go to higher correlation.
Yeah. But the only subtlety is that it is not as meaningful to look at this correlation function, because this is not engaged invariant, this is not the physical, there is no freedom, and so on. And what people usually do then, they look for the correlation function of the field strength, or if you want to think, the correlation function between electric field, magnetic field, and so on. Okay? And this uses x minus y. At least in 4 dimensions, it goes to the 4th power.
But again,
and you can normalize this. You have some tensor structure here, yeah. But an overall constant of 1.
But this will only show you that the scaling variance is not broken by quantum fluctuations or whatever. And to go to conform, you would have to go to the 3-point correlation function. No? That's what you said.
Yeah. Oh, this is just like a shortcut. But in this paper, they do a more systematic approach. Then they look into the 3-point functions and so on. Okay. I guess I've seen this paper. Right. It's something like what Maxwell theory teaches us about scaling, conformal invariance, stuff like that. I believe I sent you. I can send it the other subtlety here is that if you look this at the control level, these forms of the operator were fixed for primary operators. Okay, so and the point is that F in is certainly a primary operator. Okay, because this cannot be written as a total divergence. Something like this. It cannot be written as a derivative of some other tensor. Okay, so we use a primary. And the question of is maxwell theory away from 4 dimensions conformal? Then the point is, remember, okay, the first step, in order for you to make this classification of the operators into primary, descent, and so on, you must have first guarantee that you have the conformal symmetry. Okay, if you and this is what happens in 4 dimensions for maxwell theory, but if you move away from 4 dimensions, then you just compute this, like brute force or some other method, but not using conformal symmetry because this is what you want to check for. And you compute this, the 2-point function, 3-point function, so on and so forth. Let's say that you do not find the behavior you expect for a CFT. And you say, okay, the maxwell theory away from 4 dimensions is not conformal at the control level. Can I improve it? Can I add some other fields in the theory so as to make it conformal? Then one guide in this endeavor is just you should add some fields such to make this field strength a primary operator. Then, if you do not add any field, then you can write something like this, just with the gauge field. But then you should add some, I don't know, some scalar fields, or some maybe symmetries, I don't know, and such that you can in the end write this. But now this is not just a function of the A's, but a function of this extra field that you introduced. And this is kind of what we've done here at the classical level in 3 dimensions. And what this paper that I talked to you about does is something like this. It tries to improve maxwell theory at the control level. It tries to improve the maxwell theory at the control level by introducing new fields when you're away from 4 dimensions in order to restore or to introduce conformal symmetry. Okay, it goes along these lines. Okay, a few things I talked about here is the results I talked about from the top of my head. I might have got something mixed up here, okay, but I believe the point is clear. Okay. So any questions? Because I believe this was the last example. Yeah. And the next thing would be just to discuss, just basically to present the water identity for the scaling transformation. And then the next best thing would to discuss some example at the control level, but I do not have it prepared. It would take a long time, and to do things the right way, then you have to study the correlators and use the OPE and all that. It's a big point. So we're just going to give you the water identity, tell what it means, and if you want to check if a theory has conformal symmetry at the control level, this would be all the tests. Okay. So, and just to justify a bit more, I'm gonna just I'm just gonna give you remind you kind of how the word identities come about. I'm not just gonna write down the answer for the word identity for scaling. Okay. So, word identities. This is again not the most vigorous derivation of word identities, but it uses a pretty famous trick. We use the path interval. And I'll do this transformation. Okay, I'll take generic field and transform, and this field, and infinitesimal transformation, this field can be written like the original field plus some variation. Okay. A pre-generic variation that depends on this parameter epsilon. There is a parameter of the transformation. Okay? And the definition of the symmetry, if this transformation is a symmetry, then of course this means that the action, the variation of the action by this same transformation is 0. Okay? This is pretty much the definition of the symmetry. Okay? And the trick is, within this path integral derivation, is that you work that the variation of the action. The trick is you make just write down first. The trick is I guess there is a conventional minus sign here. Doesn't matter much. Again, on the dimensions, the point of the trick is that the variation of the action will be something like this. A will be the associated constant current. Here becomes an x. And the trick is that you make this. This would be kind of a global make as translation. You make the trick is you make it depend on spacetime, and then you are that the variation of the action can only be something proportional to the derivative of this, because then when you go back to the global transformation, then this guy vanishes and this is indeed a symmetry. This is really hand wavy, but I don't remember where I've seen this, but I've seen well, I don't know if it was a proof, but a really step-by-step explanation of this trick and how it does not leave any loose ends. Okay, it's just hand wavy, but it has some substance to it. Okay, but that is not the case yet. Okay, and the point is then that we will study this. Well, I'll introduce this notation first. X, I will use to denote n fields. So it will be this field 1 at spacetime point 1, field 2 at spacetime point 2, and so on, blah, 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 to a field n. Okay, in general, different fields at different spacetime points, or different operators at different spacetime points. Okay, so this is just a shorthand notation for any operator or any number of operators at any arbitrary points in spacetime. Okay, and what we want to consider is basically this point, this correlation function, which by the path integral is just given by the measure of the fundamental fields, whatever they are. We have here x and the exponential of your action here as in these fields. Okay, so I'm effectively just like considering any correlator that, okay, in the field. And the question is, what is the effect of this symmetry transformation here on the correlation functions? Okay, because ultimately, physically, this is all that matters. Okay, the correlation function. That's what we measure. Okay? And if I apply that transformation over there to this x, after that this becomes an x prime, then again by definition it will be something like this, where I haven't written it explicitly, but this would be from this I can define the variation delta x. Yeah, this guy has this form. It would be like a sum of the variation. Okay, if I have some space time, one, blah, 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 then blah, blah, blah. Just the sum of the individual variations of whatever operates up here says x. Okay. And then the symmetry. If it is a symmetry transformation, then it means that this coordinate cannot change. Okay, so x prime must be equal to x. Okay, the coordinate of x prime must be equal to the coordinate of x. Just the symmetry statement. And then we're gonna use that path into representation, and whatever we obtain is gonna be the word identity for this particular transformation that is parameterized by this epsilon. Okay, and then we're just gonna take epsilon to be the scaling and see what we obtain. Okay, so this just translates this. Okay. We will obtain some transformation or reaction that actually be S prime. And first thing, we get rid of the hardened piece just by making an hypothesis. We suppose the measures do not transform. Okay? Okay, well, of course, you have to worry about anomalies and so on, but we're gonna suppose there are no anomalies. Okay? The measure is invariant, basically. So I'm just gonna erase this prime over there. Okay? Now here in this x prime, use this expression. Okay? And on s prime, use. From here you can x prime, s prime is s plus. Okay. So this left hand side becomes. I'm not gonna repeat the right hand side because I'm lazy. This is something like this. And well, they actually take something like this. S plus dot S. And now we Taylor expand the exponential, the variation. Okay? Well, maybe to justify this a bit better, we write this variation. Of course, we suppose it is non-vanishing using this rate. Okay? So this variation is actually, I put that minus over there, right? So here is the nu epsilon. I'm not writing any indexes on the epsilon, but for a specific transformation, you could have some index structure over there. Like translation, there would be a delta mu, epsilon nu, and so on. Okay? Just to find out pollute too much. I'll just write the right inside of this. Okay. And we're gonna Taylor expand this. This is supposedly an infinitesimal transformation. Okay. So inside this epsilon there will be some parameter like lambda for scalings that I take to be infinitesimal, so I can Taylor expand this. Okay. So when I do this, I have 1 minus I that into the and now I just compute this, okay? This first term, this with this, just gives the original correlator, okay? It's the original field with the original action, okay? The second term will be this with this. It's gonna be careful with this factor of the correlation function because this does not involve any fields. Okay? The conserved current will typically involve the fields, so you must stay inside the path interval. Okay? And there will be now this correlator here, the transformation. Okay? This with this, and this with this would be second order in the parameter, so I do not consider. Okay? And then the right hand side is just x, so I can cancel this factor. And then I can just do the usual algebra here, and usually write it like this. Okay? Some space here because I'm going to write something here. I take this guy to the other side, so I get a plus, but then I integrate by parts to liberate the parameter here, so I get a minus sign. And so the derivative will act on this correlator. And since this is an arbitrary parameter, this is an arbitrary infinitesimal transformation, I just take a functional derivative on this parameter and just rip it off, just like we were ripping off the parameters on the n-equal tensor in the previous lecture, applying the theorem. And so when I do this on this other side, the integral manages to, okay, just obtain a delta x prime minus x. And in the end is that I would take something like this. Let's see if I do not miss. This side would be typically represented by something like this, the sum. Inside the correlation function. And this would typically be something like this. Sum over I. There will be some delta functions over here that, where the x, I is at the position of these operators. And we have here G, the generator of the symmetry. I, xi, that's this correlation function. Okay? This is typically something like this. Okay? And I guess in the convention, when I substitute this variation, this variation I can write minus I, j, or j, say for a translation, this would be minus ip, or minus I. Well, it would be this. And the translation would be minus I derivative, the mu. Okay, I might have missed some minus sign and something like that, but it doesn't matter much because I guess everyone has seen this before. I just wanted to refresh your memory. Okay? And the point is, of course, now this is the one identity, okay? For general space-time symmetry. Okay? Since this guy is expected to vanish, well, it obtains some conditions for these correlation functions. And well, let me just write for the translation with the computer. For translations, just, I guess, I'm writing this at first. The conserved current from translation is just the canonical moment of tensor. So it's Jamie. And remember, I did not write any index of the epsilon for laziness, but for translation, it is an epsilon mu. So again, set mu here. I guess a minus. We'll write it like what does this mean? Okay. First of all, I just inverted the order. I wrote the right hand side first, and left hand side. Conserved current is the canonical energy momentum tensor. So this means that first of all, probably plus or minus 0. Yeah, I don't know. And this means that this is just basically what I wrote here, where the generator is the momentum operator. And this notation means that I'm taking the nu, the derivative, in the xy position, on the operator of I and the xy position, and summing over all of these individual transformations, like here. Okay, and we get this delta function over that. That's carried over from the definition, basically. And this means that physically an insertion, if I have this operator x, that can be pretty much like any operator in the theory, a product of operators at different points. If I take this x and I make an insertion of the energy momentum tensor, then this must be conserved. This new coordinate must be conserved, except at points when that coincide with the operators inside here. Inside this x. Okay, if I insert this energy momentum tensor at the same point as some of these operators over here, then I might not get another right that this coordinate to vanish. Okay, so this is just the quantum version of energy momentum conservation. Okay, phrase in terms of correlation functions. Okay, everyone has seen this before, or something. And well, there's something for rotation, I'm not going to write it. Very interested in scalings, and I believe you can already guess what it is. It is basically, I have this x, the conserved current. Well, the conserved current would be that another conserved current that we had. When I apply these derivatives, and okay, this conserved, and I message everything, I can end up with simply the trace of the energy momentum tensor here. Okay. Well, the scaling current is something like this. Okay. Plus some internal part. Okay. And there will be this the nu here. Then apply, then I know it is maybe conserved like this. Okay, I use the previous conservation laws. And what I'll obtain in the end, in fact, is just the trace over here, and on the right hand side, I'll obtain basically the same thing with that, but now the generator that I obtain is the generator of scalings. So this means that what I get here are the scaling dimensions of these the individual operators that are inserted inside X. Okay. So the interpretation is pretty similar to the translation symmetry. It means that basically means that the energy momentum tensor is traceless, except maybe if I insert this guy at same points as any of the fields that compose the X operator. Okay. And so this, you could think about using this as maybe as a test to constrain if you're studying the OPE, and then you to use this like a test to constrain some data or something like that in the bootstrap fashion. Okay. And then there is a point to actually work out some example here. Not only I do not have it prepared, but I started to try and prepare something in the simple scales of the scalar field, but then it was getting too big. Okay, but more or less what you can argue is that you could, by applying the OPE, you can reduce n point functions to n minus 1 point functions, and so on and so forth, until you reach like, you have an expansion that is entirely in terms of the 2-point functions of primary operators, which you know exactly their form. Okay, you might not know the constants, the structure constants that appear in the 3-point functions, but you can usually get an expansion of any n point function in terms of 2-point functions. Okay, So of primaries. So say you could take X just in a scalar field theory. You could just take X to be one scalar field and we would take a 2-point function over that. And try and study that together with the OP. Okay? And I don't know if I mentioned this, but the energy momentum tensor is always a primary field. Okay? It's guaranteed to be a primary field. Why? Because if you look to its conserved charges are energy momentum. If the energy momentum tensor were not a primary field, this means we could write it as you could write it as a derivative of some other operator. And then, well, in the conserved charge, you have an integral of the entire space. And if the energy momentum tensor was could be written as a derivative, then the conserved charge would vanish. So it will have zero momentum, zero energy always. It would be a contradiction. Well, maybe not a contradiction, but something like truly like an undesirable property. And the point is, so this why the energy momentum tensor is always a primary operator. Okay? And any improvements that you can do. And so you could study all these point functions. These X operators are only primary operators that enter the X. Then you can use the formula 2-point functions, 3-point functions, and so on, and use the OPE and get some really big system of equations that maybe try and solve. Maybe some additional hypotheses like standard perturbation theory and so on. It can get big, but you can exploit this to study conformal symmetry or to test if your theory indeed has conformal symmetry. And another thing, of course we suppose that the measures do not transform, and there is a really famous anomaly, that is the Weyl anomaly, or also known as the trace anomaly. That is basically, if you're sitting on a curved spacetime, then the 1-point function of the trace, well, in order to have conformal symmetry, this must vanish. Okay? This means that the energy momentum tensor traces at the quantum level. But if you could have anomalies if you're on flat space. If you're doing two-dimensional conformal field theory, which we have not discussed, then this has a very simple form. I guess it's a 12 pi here, something like this. And it goes with the Ricci scala. Okay? So, of course, if you're on flat space, this goes away. But it would have also other sources of anomalies. And this is the so-called central charge. Okay, the theory. If you're on higher than 2 dimensions, then you can have other terms here. You still have a central charge term. You have, well, schematically, you have a bunch of tensors. You can have the Weyl tensor squared here. You can have another term with the Ricci scala squared. You have some term with the dual of the Riemann tensor. And if you at least have some additional symmetries, discrete things like parity and so on, you can get rid of some of these terms. Okay? But the most general, I guess you have something like 5 terms on this right hand side over here. And all of these come with their own coefficients. And so the value times it's an A. And C specifically has it is known from it was first discovered in 2-dimensional conformal field theories, or you can do computation much more explicitly by using complex analysis, control integration, and so on. This central charge has really deep information in the theory on your ultraviolet degrees of freedom. And the same interpretation here is over to high dimensions, but to actually do something is more complicated because you do not have you no longer have the complex analysis on your side, and also you get additional terms like this Weyl squared, the Aula tensor squared, and something like this. And those famous theorems, there is a famous C theorem and an A theorem. that concerns basically there are properties of normalization groups. Okay, in 2 dimensions, I just improvise here. Okay? This is basically the end of the lectures, and I'm just telling you some more cool stuff that lies ahead and builds up on all of these concepts. If you have theory space here, in a quantum field theory, the Z theorem is something like we have some flows here, and say you have fixed points here, and you have fixed points here on theory space. And the Z theorem in 2 dimensions, it is indeed a theorem was proved rigorously. It says you can construct a function, which is called a Z, which decreases monotonically along the RG flows, and at the fixed points, its value, the value of this function, coincides with the central charge. Okay? And it makes sense to talk about central charge because at the fixed points we would have CFTs. Typically, always as well. Okay? And this is a powerful tool to to study the matter of whether or not scaling variance implies conformal variance at the control level. And after some time, people may manage to generalize the C theorem to 3 dimensions, or is known as the A theorem. That's because you get more additional terms here, and you do some similar stuff, and so on. So that is something that can be studied, that builds up on this concept that we won't have time to study here. There are many other things that were left out. This was just about the most standard conformal field theories. There are many other conformal. You can endow your conformal field theory with additional structures, like you could make it invariant under some Lie group. You can consider super conformal theory, namely you introduce a symmetry, so you have additional structures because you have fermionic symmetry. There are a few other things called like boundary conformal field theory. There you have some system, and the system has a boundary, and the CFT lives on this boundary. And the fact that it lives on the boundary imposes additional constraints on the theory. That there's a really big vast literature. But so what I've been discussed this here were just the general features of any CFT. Okay, and if you want to know what you should take by heart from this, it's just not only, of course, everyone already knows this, what are conformal symmetries, of course, but you should know the form of correlators, 2 and 3 point correlators, and then you should know by heart the operator state correspondence that arise in CFTs. I mean, that discussion made on radial quantization, then that is basically an isomorphism between local operators at the origin and the states of the Hilbert space state. You should have know by heart also the classification of this Hilbert space and its corresponding local operators into primaries and descendants and what they mean, revolving around the lattice structure of the algebra for scaling dimensions. And everything else is basically just like playing with these concepts. And also mainly a bit more on the practical side, the OP, the product expansion, which does become an exact expansion when you have conformal symmetry, and which is the main tool of the conformal bootstrap research program. The question, I should also emphasize that this question of scaling versus conformal symmetry is also a theme of ongoing research. So it's not, the generalization of this C or A theory is not known for arbitrary dimensions. Okay, it has been proved for 2 and 3 dimensions. I guess there is some proof of 4 dimensions, but I don't think it is